Frequency response of amplifiers. Our analysis of simple amplifiers has thus far focused on low frequency characteristics, neglecting the effect of device and load capacitances. In most analog circuits, however, the speed rates with many other parameters such as gain, power dissipation and noise. It is therefore necessary to understand the frequency response limitations of each circuit. In this chapter, we study the response of single stage and differential amplifiers in the frequency domain. Following a review of basic concepts, we analyze the high frequency behavior of common source and common gate stages and source followers. Next, we deal with cascade and differential amplifiers. Finally, we consider the effect of active current mirrors on the frequency response of differential amplifiers. General consideration: Miller effect. An important phenomenon that occurs in many analog and digital circuits is related to Miller effect, as described by Miller in a theorem. Miller theorem. If the circuit of figure A can be converted to that of figure B, then Z1 is equal to Z by 1 minus AV and Z2 equal to Z by 1 minus AV to the power minus 1, where AV equal to Vy by Vx. Figure application of Miller effect to a floating impedance. Proof: the current flowing through Z from X to Y is equal to Vx minus Vy by Z. For two circuits to be equivalent, the same current must flow through Z1. Thus, Vx minus Vy by Z is equal to Vx by Z1, that is Z1 equal to Z by 1 minus Vy by Vx. Similarly, Z2 is equal to Z by 1 minus Vx by Vy. It is important to understand that equations hold if we know a priori that the circuit of figure A can be converted to that of figure B. That is, Miller theorem does not stipulate the conditions under which the conversion is valid. If the impedance Z forms the only signal path, it will X and Y, then the conversion is often invalid. Illustrated in figure for a example, this resistive divider. The theorem gives a current input impedance but an incorrect gain. Nevertheless, Miller theorem proves useful in cases where the impedance Z appears in parallel with the main signal. Figure in proper application of Miller theorem. Main signal path figure, typical case for valid application of Miller's theorem. We should also mention that, strictly speaking, the value of AV equal to Vy by Vx in equation 2 and in equations must be calculated at frequency of interest. Complicating the algebra significantly, however, in many cases we use the low frequency value of AV to gain insight into the behavior of the circuit. If applied to obtain input-output transfer function, Miller's theorem cannot be used simultaneously to calculate output impedance. To derive the transfer function, we apply a voltage source to the input of circuit, obtaining a value for Vy by Vx in figure A. On the other hand, to determine the output impedance, we apply a voltage source to the output of circuit, obtaining a value for Vx Vy that may be equal to inverse of the Vy Vx measured in the first test. For example, circuit of figure B may suggest that the output impedance is equal to R out is equal to R naught by 1 minus 1 by AV is equal to R naught by 1 minus 1 plus GMB R naught to the power minus 1 is equal to 1 by GM plus GMB plus R naught, whereas the actual value is equal to R naught if X is grounded on. Other subtleties of Miller's theorem are described in the apprentice. Association of poles at nodes. Consider simple cascade of amplifiers depicted in figure. Here A1 and A2 are ideal voltage amplifiers. R1 and R2 model the output resistance of each stage. Cin and Cn represent the input capacitance of each stage, and Cp denotes the load capacitance. The overall transfer function can be written as V out by Vn of S equal to A1 by 1 plus Rs Cns into A2 1 plus R1 Cns into 1 by 1 plus R2 Cps. The circuit exhibits three poles which is determined by total capacitance seen from each node to ground multiplied by total resistance seen at the node to ground. We can therefore associate each pole with one node of the circuit, that is omega j equal to tau j power minus 1, where tau j is the product of the capacitance and resistance seen at node j to ground. From this perspective, we may say each node in the circuit contributes to one pole to the transfer function. Figure cascade of amplifiers. The above statement is not valid in general. For example, in the circuit of figure, the location of pole is difficult to calculate because R3 and C3 create interaction between X and Y. Nevertheless, in many circuits, association of one pole with each node provides an intuitive approach to estimating the transfer function. We simply multiply the total equivalent capacitance by total incremental resistance both from node of interest to ground, thus obtaining an equivalent time constant and hence a pole frequency. Figure example of interaction between nodes. The above approach does suffer from some limitation. In particular, the simplification of circuit through the use of Miller effect often discards the zeros of the transfer function. However, the utility of the method becomes apparent in more complex topologies as described in the following example. Thank you.